Question 6, the real killing ground of this mock, which of course is the year 13 2018 mock, just for the purposes of the tape. 13 marks. 13 marks. So well over 10% of the marks on one question. And genuinely, this is a year 8 and year 10 question. Admittedly, the first bit isn't. Write an equation for the reaction of phosphorus with an excess of oxygen. You were asked to learn that and commit it to memory at the end of year 12 going into year 13. Phosphorus 5 oxide. Yeah, just go away, just learn that. But question 6, part 2, is genuinely a year 8 question. Describe a test you could carry out in a test tube, yeah, not on the moon, not in a particle accelerator or any of the fancy stuff that you wheeled out, to distinguish between sodium oxide and the product of the reaction in question 6.1. Even if you couldn't do this, you know that phosphorus reacts with oxygen probably to make an oxide. So in year 8, and I can actually even see the PowerPoint, the year 8 PowerPoint, that talks about the metals in group 1 and group 2 are called the alkali metals because their oxides and hydroxides are alkaline, and oxides of non-metals are acid. So a thing we're going to carry out in the test tube, okay, is going to be an acid-alkali test. We're going to dissolve it in water, and then we're going to test the resulting solution for its pH. Now, it's 3 marks to get here, so it's not just good enough to say dissolve in water and test for pH. How do we test for pH? So you're going to need to describe an indicator to use, and if you're using an indicator, I want the results for that indicator for acid, and I want the results of the indicator for alkaline. If you're using a pH meter, I want you to give the results for the below 7 for the alkali metal and above 7 for the phosphorus. But really, definitely a year 8 question. And talking of questions we should be able to do when we were still prepubescent, 6.3, state the type of crystal structure shown in silicon dioxide and sulfur trioxide. Silicon dioxide, we know, is the classic example of the giant covalent lattice, and we know that sulfur trioxide is a simple covalent molecule. Right, and then we're going to explain why silicon dioxide has a higher melting point than sulfur trioxide for a massive 4 marks. Okay, I really are throwing marks at you in this question. So I want a full and proper explanation. You're going to describe the bonding in silicon dioxide and why it is strong, and why therefore a lot of energy is needed to melt it, and therefore why it has a high melting point. And then you're going to compare and contrast with sulfur trioxide, and you're going to talk about the bonding in sulfur trioxide being simple covalent molecular, so it's got covalent bonds between the atoms, but very weak intermolecular forces, which are the only forces which need to be broken to melt the substance. Right? Must be able to answer this question and questions like it. A similar question, just to digress a bit, why has sodium chloride got a high melting point and bromine got a low melting point? So we're contrasting a giant ionic lattice with a simple covalent molecule. Key thing, of course, is intermolecular forces for the simple covalent molecule. Don't fall into the trap of saying that they're weak covalent bonds. I'm not breaking covalent bonds when I melt a simple covalent molecule such as carbon dioxide. The carbon dioxide stays as carbon and 2 oxygens joined together. I separate the molecules. I'm separating the molecules of carbon dioxide, so I'm breaking the weak intermolecular forces between molecules. Write an equation for the reaction of sulfur trioxide with potassium hydroxide. There's a number of different available options to you here, but it's an acid-base reaction, isn't it? So acid plus base gives us salt, and where appropriate water, but that's not going to be the case here. Write an equation for the reaction of an excess of magnesium oxide with phosphoric acid. Knowledge. It's all in period 3. We're going to be making magnesium phosphate. Phosphoric acid is H3PO4. This is all knowledge that we need to go back and learn if we didn't know. Draw the displayed formula of the undissociated acid formed when sulfur dioxide reacts with water. Well, sulfur dioxide reacting with water, again, this is period 3 stuff. It reacts like this. It doesn't make sulfuric acid, it makes sulfurous acid, H2SO3. So undissociated, we're going to have that. Question 6 was pure. Have I bothered to learn the information in the inorganic period 3 unit, coupled with some really basic structure and bonding from year 12 or year 11 or year 10?